Yeah, come in. Hi.
Hello.
Take a seat. Yeah, so how are you?
I'm well. How are you?
I'm good too. So did you take the first call from the HR?
Yes.
So you're interested in the projects that our company does, right?
Yes, very much.
Okay, so let's start.
Yes.
Good. Can you define overfitting and underfitting?
Overfitting is when the algorithm overfits the data, and underfitting is when the algorithm underfits the data.
Could you elaborate?
Sure. Overfitting is when the algorithm performs really well and makes good predictions, and underfitting is when the algorithm performs really badly and makes bad predictions.
Are you sure that the algorithm performs well during overfitting and performs bad during underfitting?
Yes, sir, 100%.
Oh, but how will you find if the algorithm is performing well or not?
We can track the performance using data.
Which data?
Your data. Oh, no, the test data.
Great, I didn't know that, so thanks for explaining it so well. So, what is confusion matrix? Can you explain this?
Confusion matrix is a matrix where we have X rows and Y columns.
Okay, can you elaborate it?
Wait. It's X and Y, simple.
Okay. Can you tell me why do we use it?
Sir, we use it to solve confusion.
Which confusion?
How would I know the confusion, sir? It's your confusion, not mine.
Okay. Can you just tell me the algorithm that we use to solve confusion matrix?
The same algorithm in which we have confusion.
Okay, I'm done.
So this is what happens when you are not prepared for your data science interview. Now let's try to understand each of the questions properly. The very first question was, what are some of the techniques used for sampling? Now first of all, let's understand what exactly is sampling. Let's say you are working for a marketing firm and your manager wants you to find out on an average how many people in India, so on an average how many people in India visited bank last year. Now if you try to understand this problem, this is a really challenging problem for you as an individual. If we look into the population for India, so let's assume this is Indian population. We have 132 crore people. And if we try to perform the survey, so let's say this is you, and you wanted to conduct a survey on each and every individual of this population, you will end up, maybe I would not say it is first of all not possible. So not possible for you as an individual. Even if it is possible, it will take a lot of time, lot of energy, plus you need a lot of money. Now this is something which a marketing company would not be interested to invest in. For such a simple question, which looks very simple right now to all of you, but for a marketing company, this is something which marketing company would not be interested to invest in, because this is a lot of task for a company. So these kind of large scale surveys are actually performed by the Indian government, which we call as census. But for a marketing company, if they are willing to find out this answer, the best solution is to perform what is known as sampling. So I'll take a small sample, and when I say sample, I basically mean I'll take around, let's say 1 lakh random people. So 1 lakh random people. And now on top of these 1 lakh people, we will perform the survey. So let's say this is my sample, and I'll call this as sample with 1 lakh people. And on top of these 1 lakh people, now I will perform survey. Now this is where the actual usage of sampling come into picture. Now once you have the result, let's say I'm having the average on this particular sample, let's say the average came out to be 52%, which basically mean out of these 1 lakh people, 52,000 people did visit the bank last year. Now using this particular average, which is also known as the sample mean, we can approximate the population mean, and this concept is generally known as inferential statistics, which we are not trying to understand in this particular time. But the objective of this particular question is to understand where to use sampling, and this is the real example of where to use sampling. Now what types of sampling we have? So if I talk about types of sampling, or maybe how many types of sampling is available to us, your sampling technique is divided into 2 categories. One is probability sampling. Second one is non-probability sampling. Now in probability sampling, the techniques like simple random sample, systematic sampling, stratified sampling, and cluster sampling comes. While for non-probability sampling, we have convenience sampling, we have quota sampling, then judgment, and finally snowball. Now it is not required to understand each one of them, because in machine learning and data science we generally not use all of them, but there are 2 important sampling techniques which are really important for you guys to understand, and I'll just mark them or maybe highlight them. One is simple random sampling, the other one is stratified sampling, and these are the 2 most important sampling techniques which we generally use when it comes to data science and machine learning. So let's try to understand these 2 sampling techniques. Now let's start with the very first technique, which is simple random sampling. In simple random sampling, let's assume that this is my sample, or maybe this is my population, and we have some random people. I am here marking each person with a number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and let's say 17, 18, 19, and 20 over here. Let's say this is my population. Now I want to perform random sampling and I want to sample out, let's say 5 observations. Now in simple random sampling, each observation has a equally likely chance of getting selected into the sample. So when I say what I mean by this, the probability of the data point number 1 getting selected into the sample is 1 divided by 20. 1 divided by 20 because I have only one such data point and there are total number of 20 data points. The probability of data point number 2 getting selected into the sample is 1 divided by 20. And this is also equal to the probability of data point number 3 getting selected into the sample, probability of data point number 4, and so on for all the 20 data points. So when we create a simple random sample, the very first constraint of creating a simple random sample is each observation has a equal probability of getting selected into the sample. And I'll just say probability of a data point O is equal to 1 divided by M, where M is the total number of observations in the population. So if I create the sample, it can be 1, 5, 6, 2, and let's say 12. So 1, 2, 3, 4, 5. This is my simple random sample. Simple random sample. Now what about stratified sampling? When it comes to stratified sampling, here when we are performing the sampling, we also have to make sure that the sample is having the observation in same proportion as it is present in my population. What I mean by this, let's take a very general example. Let's say this is my population, and here I am having let's say 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5 present in black color. I'll remove this. Let's say 1, 2, 3, 4 present in black color. Then we have 5, 6, 7, 8. That is in green, followed by 9, 10, 11, 12, 1, 2, 3, 4, 13. That is in blue and red. 14, 15, 16, 17, 18, 19, and 20. So here in my population, I'm having 4 groups. 4 groups. One group is the black group, which is having 4 observations. And here OB means observations. Then we have a green group with again 4 observations. Then we have a blue group with 5 observations. At last we have a red group with 1, 2, 3, 4, 5, 6, 7 observations. So total number is 20. The total number of data points in the population is 20. Now I wanted to create a sample. I wanted to sampling But if I use a stratified sampling, I have to make sure that in my sample, the observations are in the same proportion as they are in my population. Now, what is the proportion of black points? It is 4 divided by 20. For green, it is again 4 divided by 20. For blue, it is 5 divided by 20. For red, it is 7 divided by 20. Let's say I have to create a sample with 5 observations. So I'll take 4 divided by 20 into 5. These many observations from black sample. Then 4 divided by 20 into 5. These many observations from green. Then 5 divided by 20 into 5 from blue. Then 7 divided by 20 into 5 from red. Now if I solve this, so let's quickly solve them. 5 times 4, I'll get 1 over here, 1 over here, and this will be around 1.25 something. So it is approximately 1 only. So 1, 2, 3, and here I'll get 2 point something, so let's say 2. So my total selection, or my final selection, would be in this format. I'll take one data point from black sample. So let's say I randomly took 3 from black. Then I'll take one data point from green. Again I randomly took 6. Then I'll take one data point from blue. So let's say I randomly took 11. And I'll take 2 data points from red. So let's say I randomly took 14 and 20. Now please remember that when we are making a selection within each group, that will be simple random sampling. And that is what your stratified sampling is. So basically the concept is that your sample should consist of the observations in the same proportion as they are present in your population. Now the second question was, explain overfitting and underfitting. In order to understand overfitting and underfitting, here I have created 3 images, and I would say these are my 3 plots with the data on x-axis and y-axis. So just assume that we have a data like this. I'll draw it over here. We have some x data, we have some y data, and we have plotted it. Similarly, this is x, this is y, this is x, this is y. Now let's call this as figure number 1, figure number 2, figure number 3. Now let's try to fit different models on each of this same data. Please remember, figure 1, 2, 3 consists of the same data, but we have plotted it for 3 times. For figure number 1, I am going to plot a linear model. Y is equal to beta naught plus beta 1 of x. And your linear model, you will find out, will pass something like this. For figure number 2, let's try out a polynomial model with degree 2. Y is equal to beta naught plus beta 1x plus beta 2x square. And that model would look something like this. Then for the third figure, let's try a polynomial model with order 4. Beta 1x, beta 2x square plus beta 3x cube plus beta 4 x to the power 4. And that would look something like this. Now here, if you closely observe, in figure number 1, my model is not able to explain the pattern in the data. So this model is not able to explain the pattern in the data. While in this particular case, which is the third case, here the model is passing through each and every data point. So model is passing through each and every data point. Now please understand one thing. In this particular case, which is my third case, my model is not learning the pattern. Please remember, the objective of any machine learning model is to learn the pattern from the data, not the data itself. And in the third case, what is happening? Your model is learning each and every data point. So here, model has learned each and every data point instead of learning the pattern. And this is the case of overfitting. And I would highlight it with red color because this is the case which we always try to avoid. We do not want to build a machine learning model that learns the data but is unable to learn the pattern in the data. While the first case is known as underfitting, because here the model is not able to capture any kind of pattern. It is just passing through the data and it is not understanding the pattern in the data. So it is not able to explain the data. So it is underfitting. But the middle case, the second figure, so here you can see that the model is trying to explain the pattern in the data, the U-shaped curve. Because if you closely observe, first my data is having a decrement, then my data is having a increment, and that is what you can see over here. So this U shape, which is a polynomial model, is capable enough and it is best suited for this kind of data because it is able to explain the pattern in the data. So this is known as the good fit. If you are not able to understand even this explanation, let's take a very general example. Let's say I'm having two kids, kid number 1, kid 1, and I'm having another kid, kid number 2, kid 2. Now this particular kid, kid number 1, they both are trying to prepare for particular exam. Now what kid number 1 has done? Kid number 1 has only tried to learn from one sample paper. One sample paper. But kid number 2, what this person is trying to do, he is trying to go through various sample papers. So let's say this is sample paper number 1, sample paper number 2, sample paper number 3, sample paper number 4. Now here, when the particular kid is only focusing on one sample paper, kid number 1 will be easily able to memorize this sample paper, right? So easily able to memorize. While kid number 2, since he or she is trying to go through variety of sample papers, kid number 2 will not be ending up memorizing these sample papers, but he or she will understand the pattern. Understand the pattern because this particular kid is trying out variety. He or she is trying out variety of sample paper. Now this is what happens with your machine learning model also. So when you provide limited data, your machine learning model easily overfit. And when you provide variety of data, maybe the data which is having a lot of variance, then it is hard to overfit. So if you have understood this example, I hope you guys got the clarity regarding what are the necessary measures you can take to avoid overfitting and to avoid underfitting. Now let's understand the third question, bias and variance. If you have understood the previous question, which was regarding overfitting and underfitting, this is very simple to understand. We have the same data. Let me quickly mark it. Create the same model. So this was a linear model with y is equal to beta naught plus beta 1 of x. This was a polynomial model with degree 2, beta naught beta 1x plus beta 2 x square, and this was a polynomial model with degree 4, beta 1x beta 2x square plus beta 3x cube. Let's create the general model and let's create the overfitting model. Now it is very simple to understand bias and variance. The term bias defines the amount of error that a machine learning model will commit on the trained data. Amount of error done by the ML model on the trained data. Now if you closely observe, in my figure number 3, since my model is very much close to each and every data point, here what will happen, the actual value and the predicted value will be very close to each other. So the total amount of error will be approximately equal to 0. So here error is very less. Since error is less, bias is less. Bias less. If I go to my model number 2, here you can see that all the data points are very far away from the model. So if we try to look into the values of actual and the predicted, you will find out that there is a huge gap between these two values. So here in my model number 1, the total error would be very high. So here bias is high. If I talk about the model number 2, the between model, now here neither the data points are very far away nor they are very close, but they are in between. So it will be neither very high nor very low, but I will say it is moderate or low. So I'll say moderate or low bias for the between one, for the model number 2. That's what the bias is. Now let's talk about variance. Variance is basically the sensitivity of the model towards the trained data. Now when I say sensitivity, please do not confuse this term with the terms that we use in classification model. Sensitivity means how much attached the model is with the trained data. Let's try to understand this. So let's say, or maybe let me write the definition first. It is the sensitivity of the model towards the trained data. So let's try to understand this. In model number 3, if I delete, so when I red color it, that basically means I'm deleting it. If I delete this point, and let's say this point, if I delete these 3 points from my training data, how much my model will impact, how much my model will change if I retune it. And here you can see that my model will change a lot, because as soon as I delete these 3 data points, my model will completely change. My model will become something like this. So let me highlight it using orange color. So my model will then become like this. This is my another model, or maybe the model created after deleting these 3 data points. So since the impact is very high, this model is having high variance. So I'll write high variance. While if I look into my first model, if I delete this data point, and this one, is it going to impact my machine learning model? It is not, because my machine learning model is not at all capturing the pattern in the data. Now, since it is not capturing the pattern in the data, my model post deleting these data point will also not change. And since it will not change, the variance is very less. So low variance. If I talk about the middle one, again the same case. If I delete this one, and this one, my model will neither impact very high, the impact will not be very high, the impact will not be negligible also. It will be a moderate impact, not very high, not very low, somewhere in the between. So that is known as the moderate variance or low variance. Moderate or low variance. And that is the model which we always look for. A model with low bias and low variance is what is the target of any data scientist. So good model. We always target to create a model which is not having high error. Also, it is not over dependent on the training data. And that is what the definition of, or the explanation for, bias and variance is. So let's now try to understand the fourth question, which is, what is confusion matrix? You guys must be confused about it, right? Don't be. Let's try to understand it. What is confusion matrix? It is basically like any other matrix, but with significant amount of information. Here I'm going to take the example regarding binary classification. Binary classification. Now, what is binary classification? Binary classification basically mean that I'm having two classes. One is a positive class, while other one is a negative class. Generally, positive classes are represented as 1, while negative ones are represented as 0. Please remember, this is the general case. I'm not talking it is the always case. It is general. You can change it also, but here my assumption is I'm taking positive as 1, negative as 0. Now if I compare the actual and the predicted, so let's say I'm having my data which was having pattern like this, or maybe the data structure was, it were having some independent variables x1, x2, x3, y, and y was my binary variable, so 0, 1, 0, 1, and it is also the target variable. When I provided this data to the algorithm, and here I'm assuming any classification algorithm, there are multiple classification algorithm. Let's take logistic regression for example. Logistic regression. It will return us a particular model which we call as a machine learning model. Now this machine learning model can make predictions. So there can be 4 possible scenarios. This is my y actual and this is my y predicted. So there can be a scenario where your actual is positive, which is 1, prediction is also positive, actual is negative, prediction is also negative, actual is positive, predicted is negative, actual is negative, prediction is positive. So these are the possible cases which can happen, or the misclassification and the correct classifications that can happen. Now how we name them? It is very simple. These 2 cases, since they are correct, we call them as a true case. These 2 cases, since they are incorrect or misclassification, we call them as false case. So I'll write T in front of them and F in front of them. Now based on the predicted label, I'll fill the other half. 1 stands for P, so I'll write P. O is negative, so N. O is negative and 1 is P. So these are the terms which I use for each of the classification. If a positive class is predicted as positive, we call it as true positive. If a negative class predicted as negative, we call it as true negative. Positive predicted as negative, false negative. Negative predicted as positive, false positive. It is very easy to remember them. Just focus on the predicted label. So let's say somebody asks you that let's say a particular patient was having cancer and the machine learning model predicted cancer. So predicted cancer means the machine learning model predicted positive class. So it is P, positive. Now since this is a correct classification, this is true. So TP means true positive. This is how you can remember it. Now a particular data will have a lot of such cases, right? So if I expand this data, the data will have a lot of such cases. Let's take 10 or maybe a data with 10 data points. I'm only going to draw y actual and y predicted. Y actual, y predicted, and these are my independent variables over here. So I'm having x1, I'm having x2 and so on, some more independent variables over here. Let's create a table with 10 such observations. So 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. Let's fill this table. So 1, 1, 1, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 0. Now what is the meaning of this? A particular label or a particular observation which was positive was predicted as positive. A particular observation which was positive was predicted as negative. Now let's call them, or maybe let's name them as per the term that we have learnt over here. So this is my true positive, this is my false negative, because the outcome is 0, which is negative. So this is again false positive, true negative, true negative, true negative. This is false positive, true positive, and finally this is false negative. Now how we can arrange them so that we get a one eye view? The best solution is to place them in a matrix. Let's place them in a matrix. So here this is my actual, this is my predicted, this is, let's say, 0 1 0 1. Now when 0 is predicted, sorry, when 0, the actual 0 is predicted as 0, this is known as true negative. When the actual 1 is predicted as 0, this is false negative. When the actual 0 predicted as 1, false positive, and this is true positive. Now I'll just fill this table with the actual numbers that I have over here. So how many true positive I'm having? 1 and 2. So I'll write 2 over here. How many true negative? 1, 2, 3. So 3 over here. False negative? 1, 2, and false positive? 1, 2. And this is what the confusion matrix is. So basically, confusion matrix are very helpful when you wanted to get a summary about how many misclassifications were done by the model and how many correct classifications were done by the model. Also, it can help you to perform calculations of various metrics like accuracy, precision, recall, and so on. Now let's come to the last question, which is what is cross-validation? In order to understand this, we will first of all understand the general machine learning process. How a machine learning process looks like. It starts with the historical data. This is my historical data. Now please remember that this particular data will have your various independent variables and the dependent variable. We normally break down this data into two samples. One we call it as a train sample. The other one as test. So train is generally 70%, test is generally 30% of my complete data. I'm talking about a general workflow, general pipeline. Then I use the train data to pass it. Then I use the train data and provide this data to the algorithm, the machine learning algorithm. Now machine learning algorithm will try to learn the pattern, will try to learn the relationship between your independent and dependent variable, and it will finally return you a model, the machine learning model. Now we will test this model on the test data. So I'll come back to my test data to perform testing. So testing the model performance on test data. Now if the model performance on the test data is not satisfactory, I'll go back to the algorithm to retune it. And then I'll again get a new model which I'm again going to test on the test data, and I'll keep on doing it until and unless my machine learning model start working satisfactory, start working good for both train and test data. Please remember one thing, in this particular process we are subconsciously making our machine learning model remember or overfit both train and test data, because here what we are trying to do, I'm trying to build the model on train data, test the performance on the test data. If the performance is not satisfactory, I'm again retuning the model and again testing the model on the test data. This cycle is again and again happening until I am satisfied regarding the performance of the machine learning model on both train and test. And this is a problem because due to this problem, we are not getting a generalized model. We are getting a overfitted model which is overfitting both train and test. If you are not able to understand this, let's take a very general example. Let's say I'm having two chefs. This is chef 1 and this is chef 2. Now both of these chefs are trying out a new dish. Let's call this dish as dish A. Now what chef 1 has done, every time chef 1 is trying out or preparing this dish, he or she, or maybe let's take he only, he is always making his friend, his very close friend, let's call this as F. So his very close friend to test this particular dish. And chef 1 is able to receive the feedback always from the same friend. So this is feedback. Let me again explain you this situation. Chef 1 and chef 2 both are trying to prepare a new dish which is named as dish A. Now every time chef 1 is preparing this dish A, he is only making his very close friend to taste it, and based on his feedback he is making the changes. He is doing this thing only with one friend. Like assume that I am cooking a dish and I am only making my friend to taste it, and I am getting the feedback from my friend and making the changes on my dish. Now what will happen at the end? Will I be able to make that dish loved by everyone? That is not going to happen because that dish has been crafted, that dish has been curated according to the preference of my friend. So this is the problem which is happening with chef number 1. So the final dish that chef number 1 will get will be loved by only his friend. While what chef 2 has done, he is making his dish tested by or tasted by every customer who is visiting his restaurant. So let's say I am visiting the restaurant which is owned by chef number 2. With all the dish that I am ordering, chef 2 is also asking me to try out this new dish and to provide him with the feedback. So every time a new customer, let's say customer 11, customer 12, customer 13, customer 14, customer 15. So all these customers are coming to his restaurant and he is asking each of the customer to provide the feedback. So he will get various feedback. What is wrong, what is good, what is bad. He will get various feedback. And if he implements all these feedbacks, he will be able to create a generalized dish. A dish which is liked by everyone. Now that is what the problem with machine learning modeling is. When you try to train the machine learning model against one sample, which is one sample train, one sample test, your machine learning model subconsciously remembers both train and test. And that was happening with chef 1 also. But if you present your machine learning model with variety of sample or variety of training data and variety of test data, your machine learning model will be able to learn and generalize it. Now that is where cross validation comes into picture. So what happens in cross validation? We have this data. Assume that this is my complete data. This is my complete data. And when I say complete data, that basically means complete trained data. Now what we are going to do? We are going to divide this data or chunk out this data into multiple sub data frames or sub samples. So 1, 2, 3, 4, 5. Now why I am using 5, I'll tell you. Let me just quickly draw it. 1, 2, 3, 4, finally 1, 2, 3, 4, 5. Now assume that in the first iteration I will consider this as the test data, the red one as test, and the rest of the sample. So let me highlight everything. This is my sample 1, sample 2, sample 3, sample 4, sample 5. So I am going to use sample 1 as test, while sample 2, 3, 4, 5 as train. In iteration number 2, I'll use sample 2 as test. Then in iteration number 3, I'm going to use sample number 3 as test. Then in iteration number 4, I'm going to use sample number 4 as test. And then in iteration number 5, I'm going to use sample number 5 as test. So here let me just quickly highlight all the test samples. Please remember, red color represent test data while blue color represent the train data. So red is test while blue one is train. So in my iteration number 1, I'm using sample number 1 as test while other sample as train, and iteration number 2, sample number 2 becomes test, and so on. Now here what is happening? Of the same train data which I was having previously, which is this one, we have created multiple sub data frames or sub samples, and now I am not providing my machine learning model with the complete data or complete train data, but a chunk of the data, and left out region I am using it as test. So every time my machine learning model is learning something, we are testing the performance of the machine learning model on a new test sample, and this way we'll be able to evaluate the actual performance of the machine learning model, because every time the machine learning model will be tested on a new test sample. This is what the concept of cross validation is and why we need cross validation. So that was it for this particular video. I wish you all the best for your upcoming interview. Before you end this video, don't forget to give this video a big thumbs up, share this video with your friends, and don't forget to subscribe to our Scalers YouTube channel. I'll see you in the next video.